All right, hello and welcome to a new week. Have a bit of a potpourri of topics for you today, but they're all along the lines of logic. So proving things formally using like pure logic and also more informal kinds of logic. All right, so we'll talk about both, and I guess let's just go ahead and get started. So the first thing that I want to teach you about is this magical thing called deduction and induction and the difference between them. Okay, because computers can do one thing very well. Computers are really good at deduction. Computers are super good at this. And then induction is something you do more in your daily life. Like, it's a more human kind of thing. More human-y. Okay, so I want to tell you about the difference between those things, and this is all in the context of making some kind of argument. Okay, so we're arguing with somebody about something, and we want to figure out what it means to make your argument correct. Okay, so let's first talk about that in terms of deduction after we learn about what deduction is. So an argument is deductive, we say, when the conclusion is like a certainty. It is something that is going to definitely be the case if the premises are true. So there's parts of an argument, and let's define those. So an argument, it's made up of premises, so like things that you're assuming, because premise is just a fancy word for assumption for no good reason. And then from these premises, you're trying to prove this conclusion. Okay, you're using them in that way. And so if you have a deductive argument, that means that your conclusion was a certainty. Okay, so like you have a bunch of premises, P1, it's some kind of argument, it's some kind of thing you're assuming, it's like a cloud. So you got P1, you can use that. You can use P2, it's another premise, P3, there's a third premise. You can use all of those to prove what you're trying to prove, your conclusion. Way down here. And it's always going to be true if the premises are true. Okay, so you're using all of these to make it very clear that your conclusion is always true. Okay? In every particular case. So here's an example argument. So the premise one, so these are two premises and a conclusion. So I'm using these two premises, to prove this conclusion. So the first premise, it's sunny in Fresno. Okay? That's case one. Let's assume that. And then premise two is, if it's sunny in Fresno, then Lawton won't be carrying an umbrella. Okay, that's kind of logical. So the idea is, these kind of both go together, and so when you put them together, they kind of imply this conclusion. Because we would like to prove that, oh yeah, so Lawton won't be carrying an umbrella, obviously. Okay? And this is very declarative. It's a certainty. It will always be the case. If this is true and this is true, then this must be true. That's the idea. Okay, so that's deduction. And it's kind of the opposite of induction. Okay, so induction, not to be confused with mathematical induction, if you've learned about that in a fancy math class. Induction is more about like probabilities. Okay, so we say an argument, it's inductive when the conclusion is very likely. It's not definitely the case, but very, very likely. Okay, so here's an example inductive argument, and I think we like to use induction a lot in our daily lives. So here's our premise, our thing that we're assuming. Every time I've walked by that dog, it hasn't tried to bite me. This is good. Must be a good dog. So our conclusion then is, okay, the next time I walk by the dog, it probably won't try and bite me. Yeah? So if we assume this, imply this, is it true? Well, usually, yes. In 99% of the cases, it's probably going to be true. Like, yeah, the dog's not going to bite me if I walk past it, because obviously the dog is not that unfriendly. But maybe the dog has had a bad day, or just came back from a fight with another dog. There might be still a 1% chance that the dog's going to bite me. Okay, it's not a certainty like it would be in a deductive argument. Okay, that's the huge, huge difference, and I hope you see it. Okay, so that's deduction versus induction, and let's keep trucking. More argument stuff. So validity and soundness. Okay, so let's see here. These are two different ways to describe an argument. One kind of is part of another. Let me just tell you right now that soundness is stronger than validity. So when I talk about these two, soundness is the winner if they both had to fight. Stronger than validity. Okay, so I guess the question I'm going to answer for you in this little subsection is, I have an argument, I don't like this argument. How can I attack it logically without like screaming obscenities at the person I'm arguing with? Okay, so that's the idea. Let us get started. So validity and soundness, what in the world do these mean? Okay, so an argument is valid if it's impossible for the premises to be true and the conclusion to be false. So remember, premise is just a fancy word for assumption. Yeah? Yeah, assumption. So that is what it means to be valid. And remember, this is all going back to the idea of truth. So that's going to haunt us. So we need some kind of definition of truth to begin with, unfortunately. But I think we have one in our minds, and we can use that one. So that's a valid argument. It's impossible for the premises to be true and the conclusion to be false. So if these are all true, the conclusion must be true. Okay, that's the idea of a valid argument. It's a deductive kind of thing, you see. And then we say an argument is sound if it's valid, so it has to be valid in order to be sound, and all the premises are true. Okay, that is key. So that and right there is the kicker. So here are some examples. Okay, so here is a sound argument that every philosophy class likes to use. So we have two premises. They're kind of unstated. Like nobody says like, okay, this is my premise, here is my conclusion. We just speak English to each other, right? So these two are premises, and then there's like a line separating it from the conclusion. Therefore is like a normal conclusion making word. Yeah. So you got your premise 1, let's say 1, 2, and then C for conclusion. So this is a sound argument because, well, it's got to be valid, so let's check validity on this argument. All men are mortal, Socrates is a man. If those are true, then Socrates is mortal. Must be the case. Okay, so let's prove that this is valid. Let's assume that this is true. All men are mortal. Okay. Socrates is a man. Ooh, but all men, if Socrates is a man, all men are mortal, that means Socrates is immortal. Yeah? See that play by play? So that means, yes, this is totally valid, because this follows naturally from these two assumptions. Yeah? Now, in order to be sound, it has to be both valid, so yes, it's valid, and all the premises must be true. Are they true? Is it true that all men are mortal? I think so. And is it true that Socrates is a man? Well, maybe I should say was, because he was alive back in the day, but I think that is also a true statement. So, it is therefore true that this argument is sound. Yeah? All the premises are true, and it's valid. All right. Here is a valid but unsound argument. Are you ready? So again, we've got some premises. 1, 2, you can pick them out yourself, and then a conclusion. I like to draw a little line between them to show the difference. Okay, this is a valid but unsound argument. So let's prove it's valid. So everyone who watched Hamilton enjoyed it. Okay, we're assuming that. And then John watched Hamilton. Okay, and then from that, okay, John was. If this first statement is true about everyone, then it's definitely true about John. So he watched Hamilton, so he must have enjoyed it. Yeah. So the conclusion is implied by the premises. That's not too bad. So it's totally valid. I hope you can see that. But maybe this is true, but this is not necessarily true. Okay? Some people are just not fans of Hamilton, unfortunately. So I don't think that this is going to be true all the time. So, if only it were, but this kills the soundness of the argument, though it is still valid. Okay? So in a world where these were both true, then yeah, it's totally true that John enjoyed Hamilton, but we're not in that world, probably. Okay. So, that is validity and soundness. And now it's time for you to try. So I'm going to give you a bunch of little arguments, 4 of them, and I want you to pause the video, try them yourself, and then we'll come back and explain them together. Okay? So first one, tell me if this argument is valid or sound. So if you want to prove that it's unsound, you'll give like a counterexample, something for which it's not true. Okay? Dun, dun, dun. So that's kind of the game. To prove something's false, you always want to find a counterexample. Okay? I'll use red for bad. Okay, so think about this for a second. Maybe think about it in terms of counterexamples, and we'll come back. All right, so what did you think? Let's first check validity. Is this a valid argument? So again, we have 2 premises and a conclusion. So let's assume, okay, all birds can fly. Sure. We're assuming that. Bats are birds. Are they? So, all right. If we assume both of these, in that case, then I think we can therefore conclude that bats can fly because let me get rid of all these circles. If bats are birds and birds can fly, then bats can totally fly. Yeah? We're assuming these, trying to prove that in every case. So I do believe that this is a valid argument. Yes, checks out. Is it a sound argument, though? So if it's valid, it has to be valid, and these both have to be true. I'm not actually sure if bats are really birds, so you might want to check that on Wikipedia, but that's okay because I have a counterexample for this one. Dun dun dun. So it's not true that every bird can fly because those poor little penguins, they do not have the power of flight. Yes? Right? Like the dodo bird or whatever those things were, they also couldn't fly probably. Yeah? So this is not a sound argument. Maybe I should go back to red and put an X through this. So it is valid, but it's not sound. Okay? And I hope you see that. All right. So let's move on. Let's try this one. Is it valid or sound? This argument. So again, we got 2 premises and a conclusion. Can you use these 2 premises to make this conclusion true? So let's check validity. Is this possible? Okay. All cats are mammals, all dogs are mammals. So assuming that, can we use these to prove that, therefore, yeah, all cats are dogs? And I think you'll find that even if we assumed both of these, which happen to be true, we can't use them to prove this. Yeah, it doesn't make sense. It doesn't follow, we say. So it's not valid, and because it needs to be valid in order to be sound, it's also not sound. Okay, so I hope you got that. And yeah, not too bad. If we had like assumed something over here, like I don't know, if we assume that all cats are dogs, then we can totally prove that all cats are dogs, something like that. Watch out for the assumptions, because sometimes the universe works differently, and it's a valid argument when it's just not sound. Okay, so that might trick you a little bit. Just be on the lookout. Okay, try this one. Valid or sound? If someone was a philosopher, then they weren't a historian. Well, Socrates wasn't a historian, so therefore Socrates was a philosopher. Is that a valid argument? Is that a sound argument? Okay. So, what's happening here? What's going on here is this first premise is a mouthful, so let's pack it apart. Let's unpack it. So if someone was a philosopher, then they weren't a historian. So we can use our some logical symbols to make this the case. So like if you knew that somebody was a philosopher, then you knew, if I just introduce this arrow to you, you knew that they were not a historian. Yeah? With that fancy not symbol. So remember that? So if someone's a philosopher, then they were not a historian. So it's like saying, you give me a philosopher, and I have a proof that they're not a historian. Okay? So that's the idea. You can go in this direction is the hope. But this is saying, all right, Socrates wasn't a historian, so we got this is true. And then we're trying to conclude that Socrates was a philosopher this way. So we're trying to use this kind of if-then statement, which goes in this direction. We're trying to use it backwards, which is not logically a good thing to do. So it doesn't make sense to do that. I think if you think about it long enough, you'll find that you cannot go back in this direction. That way doesn't work. This way works. So again, it's not valid. That's unfortunate. So you cannot use these two things to conclude this one. Okay, it's a bit more tricky, but that's hopefully coming to you. So it's not valid, and therefore it can't be sound, because in order to be sound, it must be valid first. Yeah? It's a stronger requirement. Okay, let's keep on going. One last one. Are you ready? So try and take a second, see if you can prove that these things are valid or sound. So we got premise 1, premise 2, and our conclusion. All right. So all computer scientists like to dance salsa, so we're assuming that that's true. Some men are computer scientists, okay? We're assuming that's true. And we're trying to conclude that, therefore, some men like to dance salsa. Okay? Let's see if we can do this. So this is saying, if you're a computer scientist, CSCI implies you like salsa. So we're kind of, if you tell me you're a computer scientist, then I can tell you that you like salsa is the idea. Some men are computer scientists. So like, if you're a man, then sometimes you're a computer scientist. Okay, and the idea is to use this and this together to prove that, therefore, some men like to dance salsa. So if you're a man, you might be in CSCI, and there's some of you, but everybody in CSCI likes to dance salsa. So you can follow this chain. You can follow the chain and conclude, therefore, some men like to dance salsa. Yes? So this is a valid argument. Dun, dun, dun. But it's not sound, I don't think, because not all computer scientists, unfortunately, do not like to dance salsa. So that one's not true. Boop, boop. So it can't be sound, but it is valid. If we were in a universe where this was true, then we can totally prove the conclusion. Okay, I hope you've you got that. Please yell at me if it's not making enough sense. I'll be happy to make up some more fun examples. Okay. So that's validity and soundness, and this is how you pick apart an argument. You can be like, okay, yeah, maybe your argument was valid, but we don't live in the universe where those assumptions are true, dude. That is a good way to attack an argument. All right. So with that power, I introduced this little arrow thing, and that arrow can be explained logically. In fact, it's called implication, and I want to teach it to you now. We had to wait a little while. I didn't want to teach this to you in the circuits lecture because it's a bit more complicated. But you're ready. You are ready now for this. Let us begin. So the idea is English is really ambiguous. What does it mean to say, okay, if this then that? How do we unpack that logically? And the way that I'd like to introduce it to you is think of truth and false, true things and false things as things that went your way and things where you were lied to, okay? Think of false as you were lied to. And true is you weren't lied to. All right, so here's what I'd like to express logically to you, and let's just go through it. So Dad's saying, hey, son, I will give you $20. Hey, Lon, I'll give you $20 if you mow the lawn. Okay? So that's what he said, and there's an if in it. What are we going to do about this little if? So we would like to come up with a logical symbol. We want the arrow, right? To represent if, and we want to figure out when this statement is true and when this statement is false. Okay? So what I'd like to show you is false is the same as thinking about the idea that you were lied to. So to figure out when the statement is false, let's just figure out under what conditions would we feel cheated? Like, Dad, why would you do this to me? If we didn't get that $20. Okay, so how? That will tell us when it's false. Well, that'll tell us when if is false. Okay, so let's think about this. So here are all the options. So again, it's a truth table. We'll come up with the real symbol soon, but here are our options. So here are all the possibilities of us mowing the lawn and getting $20. So there's 4 options total, because these can each be true or false. So we mowed the lawn, we got 20 bucks. We mowed the lawn, we didn't get $20. We didn't mow the lawn, but we got 20 bucks. And we didn't mow the lawn, and we did not get $20. Okay, so under which of these rows would we feel cheated? Okay, so because this is like, if you mow the lawn, then I'll give you $20. That's what it's saying. There's an arrow like that. So when would this be false? When were we lied to? Okay, if we assume that this was true. Okay, so let's go through this slowly. This one and this one. So we mowed the lawn and we got $20. Did we feel cheated by Dad? No. I did the work, I got my money, I'm happy. How about, we'll come back to this one because that's the real one. How about we didn't mow the lawn, but we got $20? It's like we won the lottery, right? So we don't feel cheated because Dad was just really nice to us and we got our money for free. Sounds good. How about this case? We mowed the lawn, but we did not get $20. Do we feel cheated? Were we lied to? And the answer is no, because we just didn't do the work. We probably would have got the $20 if we actually did the work. So in this case, this is the one case where we feel cheated. We mowed the lawn, but Dad didn't give us $20. Why would he do that? So that is the one case where this if statement in logic, we call it implication, is false. So this is the truth table for if. True, false, true, true. Okay, this is the one case where it's false because you upheld your bargain, but you did not get the conclusion that you were hoping. Okay, that is implication in a nutshell. So let's talk about it in real life now. Let's talk about it logically. So implication is the logical form of if A, then B. It's saying if A is true, then B is also true. Okay, so that is if A, then B. We call it implication. That's the fancy symbol in logic. All right, so it's a logical term for an if-then statement. Maybe I should put these in bold. In programming, we call this a conditional. So it's like your if-then block in Scratch. Whee. How about I draw that just to remind us when you look at this to study. So it's like your little if-then block. If blank is true, then do this thing. Okay, you can also have else, of course. So what we did on the previous slide, you might not have thought it, but we just discovered its truth table, okay? And that is actually how we can prove now if A then B is true in logic itself. Okay, so yeah, if we want to prove that if A then B is true, or A implies B is true, we just show that it's impossible to fulfill the if part. Like we just show that it's impossible to be in this one case right here. It's impossible to fulfill the if part and not receive the then part. Yeah, that is the idea. This is the if part. This is the then part. So A, we get A, but we don't get B. That's the one time that things go wrong. So if we just show it's impossible to be in this case, like if we had the thing, then we totally get the thing, then it's true. The whole thing, the whole if statement was true. Okay, so alternatively, you can think about this as if I give you A, then you have to give me B. Like it's a requirement. It's like a contract. It's implied. Yeah, that is the hope. So let's go back to deduction now that we have this symbol under our belts. So here is the same argument twice. So all men are mortal, Socrates is a man, therefore Socrates is mortal. And here is it translated into logic. Okay? So the idea is, let's prove that this is valid. Let's prove that this is valid very quickly. All right? So we're now assuming man implies mortal. You see that? This is how you can turn this into logic. Man implies mortal. If man, then mortal. That's the idea. So we're assuming that this is true, and then we're also assuming that this is true, right? So these are all assumptions. These are premises. We assume it's true. We assume that's true. Those are our assumptions. Then we prove that this is true. Okay? It must be the case. And we can just read this answer off. We can prove validity of this argument very, very quickly because we can just read it off of the truth table. We know that this is true. We know that this is true. So we must find out that this is true. So if we go back, A is man, B is mortal. I know that this is true, and I know that man is true. Yeah. I know that this is true, and I know that this is true. In every row of this table where this is true and this is true, there's only one. This must be true too. And oh man, yeah, it is. So it's automatically a valid argument. And this follows from the truth table, all right? What do you say? Follows from the truth table for implication. Like we found the row where this is true and this is true. There might be multiple. And then we showed in every case, yeah, this one's true too. That is validity very quickly. Now that we have logic under our belts. Quite nice. Okay. One last secret. One fun thing is, now that you know about like functional completeness and all that, can you draw a circuit diagram for implication? You might be wondering, is there a way to be like, oh, I have my A wire, I have my B wire. What's the box? What does it look like where I do some stuff and like it takes those things and like combines them in some way? So there's like a question mark box and it gives back somehow the result of A implies B. Does that exist? And the answer is yes, you can always make things in terms of and or not. Yes? So let me prove to you that this is the same as the following. If I add this little row right here, this is actually the same as, it's logically equivalent to, let's make it better, there we go. This is logically equivalent to not A or B. Let me prove that to you. So, not A is false or B. Okay, that makes the whole thing true. Nice. That is a T. Nice. Okay, not A or B. So false or false. Okay, that's the one time it's false. Not A is true. Doesn't matter what this is. Not A is true. Doesn't matter what this is. Always true. So, you see how these are equivalent? These are the same. So that means this is equivalent to this. And so, if you wanted to make a circuit for implication, if you want to put in some A's and get back, hey, is it true that A implies B? You just have to use not and or. Okay, you can combine them that way. That's all you need to do. So, yes, you can draw a circuit diagram for implication. And so we are trucking along, and we are ready for the next concept. So it's not farming, which I spelled the first time, and I thought it would be funny to preserve that until the end of time. It's called framing. That is what I'm about to talk to you about. And it's more of informal arguments. Arguments that you make with humans, not computers. Okay? So what I'd like to answer in one slide is, why in the world can't this person see my point? It's so obvious that this thing is true, that this thing is correct, that this thing is right to do, but this other person over here doesn't think the same way, and they're just wrong. It's so obvious that this thing is, that my way is right. What's going on? And the answer is framing, okay? A frame or a frame of reference is how you view a situation, how you view the world. So the frame that you're thinking in, the frame that you like grew up in, and that you've been taught to think inside of, it shapes very much how you view the world and all the assumptions that you're willing to make. So note the word willing. Like, you're not required to make any assumptions, but you have to be willing to make them. Okay? And this is sometimes called your worldview. I think that's all one word. So this is what framing is all about. Okay? And so if you're ever making an argument and you really want to win it, if you can find a way to control the frame, then you have the argument at your fingertips. You can control the entire argument at that point. So the idea is someone can have the exact opposite viewpoint as you, and they can justify it, which is a lot of times hard to believe. It's very unfortunate because we all think one thing, and it frustrates us to see other people think another way. But we have to take a step back and understand they're thinking in their frame. That is the idea. So what I'd like to show you, or what I'd like to teach you, is the ability to see this. All right? So let's talk about frames in politics, because that's extra applicable today. And everything I'm about to say is very simplified. Okay? This is all essentially memes about both sides. So just keep that in mind. I'm not like trying to trash anybody's opinions. So these are frames in politics, and you can see how you can argue and justify things based on this frame. So as far as abortion goes, left-wing people think in terms of, okay, I'm pro-choice, whereas right-wing people think, okay, no, I am pro-life. There's a huge difference there. You see that? Just the way that you frame the argument makes you think in a different way. It's fun to think about. That's how it works. Single-payer healthcare versus socialist healthcare. All right? So the second you say a certain term, choice, life, single-payer, socialist, it makes people think a different way. Okay? It brings up associations in people's minds. It's very, very weird, but it works. That's just the way people's worldviews work. Innocent refugees versus potential terrorists. You see the disconnect. Both sides think one thing, and they're obviously not willing to meet anywhere because they're correct. You see that? This is why politics break down. Undocumented workers versus illegal aliens. The second you say workers, you think, good, yes, we need those. The second you say illegal, the second you say aliens, you think, bad, no, get rid of those. You see that? Free speech versus giving cover to Nazis. That is something extra applicable these days, huh? So the idea is, all of these things, whatever you would like to prove to someone, you can, if you can control the frame, okay? If you can argue that, yes, this is what we should call this thing, or this is what we should call this thing, then the argument is yours. Because the second you say certain words, people start thinking in a certain way. So that is your frame of reference, and I want you to be very, very aware of it when you watch like a political debate these days, okay? The second people start saying words, unpack those words, okay? That's one of the few things I would like you to get out of this class, if nothing else, so that you can be your own decision maker, okay? Don't let the frame control you that somebody else made. All right, so that is my rant. Let us move on now to more computational kinds of things again, and that will be the end of this lecture. So state machines are a fun thing, and they allow us to like package up computation in a nice, cute little way. And you've used them before. You have thought in terms of a state machine, I'm sure, and it's quite easy actually to make a program that models these things. So the question that I'd like to answer for you in this little subsection is, how can I break down the process of computation? There are many ways, and I should highlight that. So we want to break something down. we want to like make a bunch of pieces, make a bunch of little code blocks, yeah, that like one comes after the other, and they eventually lead to what we want way down here in rainbow colors. Yeah? How can we do this? How can we break down the process of computation? The word algorithms comes to mind. That's essentially what I'm trying to give you, an algorithm for breaking down things. An algorithm is breaking down something. That's giving a step-by-step way of doing things. Okay? So, a state machine is one way to break down computation, and it's one way to think about a process or an algorithm. Okay? So, let us begin. So a state machine, they kind of look like this or this. I'll try and zoom in a second once I explain them. We say that they abstract processes. Okay, there's something that needs to happen, and you got some things that you got to do to get it to happen. Okay, that's my hand-wavy definition. So, for example, let's say that like you're born in your house. That's where you start, and it's time for you to I don't know, wake up. You have to go to sleep. You have to go to work. So you start out at home, and that is your state. Okay, you're always in some kind of state, we say. So that's like your start state. If I put the arrow here, that means you start there. You start like a new day. You wake up in your house, and then you can move around between other states via transition. So when something happens, when an action takes place, okay, actions cause transitions. You move around. So you start out at home, and maybe, well, it's time to go to work. So how do you get there? How does this happen? How do you become in the work state? Well, you can take the train. If we lived in a city with like a subway. So you take the train, now you're at work. And you do your work, you stay there, you stay inside of the state for a while, and then it's time to go home. It's time to eat dinner, time to go to sleep. So you take the train back again to get back to the home state. You see where I'm going with this? It's not too bad. It's just a graphical way of talking about processes. Just any process that you can think of, you can probably make a state machine for, and it might help you. Okay, so then you're at home, and okay, you had your dinner. Now it's time to go to bed and start this whole monotonous process over again. So you go to sleep, and sleep puts you in the bed state, and then you wake up, and, well, hopefully you wake up in your house still, and you're at home again, ready to follow all of these things. Maybe you take a nap. It's the weekend. You can follow all these states in order. Oops. And I hope that makes sense. So a state machine just abstracts processes, and these can get complicated. So if I zoom in here, this is like the state machine of like the Uber app or something, or the Lyft app. If I can scroll without it changing the there we go. So like, I don't know where you want to start. Like maybe you start here, and okay, you're like, Uber, Lyft, take me to Trader Joe's or something. And okay, now the app is in the trip requested state, and it's going to make sure that your credit card works, so it tries the payment state. If it fails, then you're back in the trip requested state, and you can enter in a new credit card or something. If the payment works, a driver gets assigned to you. They'll come pick you up. If the driver doesn't like your rating or something, they will cancel and you're back in this state. So you see how you can play this game, and you can write any kind of process in terms of a state machine. Hopefully that's not too bad. So now a driver has been assigned to you, and you're going to take the trip, and eventually the trip is going to be complete. And now from the driver's perspective, the driver gets unassigned, so he's ready to like give somebody else a ride. Or if the customer cancels, coming out of nowhere, and the driver is also unassigned, and then eventually you're at the end of your trip. So all these things, these are different states that you can be in, the state that your program can be in, and they're caused by certain actions, sometimes coming out of the ether. So that is the idea. That is a state machine. And if we could just program this kind of thing, it'll make our lives easier, because like we'll make sure that it's impossible for you to be riding with a driver and having your payment not having your payment fail, things like that. you can prove some nice properties about things if you put them in a state machine form. So that's all I want to say there. Sorry. So let us have a quick little example, 2 of them. So the idea is that you group your program into states when you're making a state machine, and then actions that happen on those states or for those states. So let's pretend that this is you. So as a student, I think of you as a 2-state machine. You have a learn state and a practice state. And this is where you start. This is your start state. That's your initial state. It's learn. And then you alternate between those 2 states. When I post something, or like I assign some assignment, and that's how it works. So like you're learning, and then it's ready for you to do something. So ready for you to practice it. So I release an assignment, and that'll put you into the practice state. You see that? And then you'll just keep on working on it until you're done with it. And so you'll stay in the state while the assignment's not finished. Do you see that? So as long as you're not done, you stay in the same state. That's okay to have a self loop like that. And then maybe you've practiced enough, or I release a lecture. Then you can go back into the learn state to watch the lecture, things like that. And then hopefully you watch the whole thing. Doesn't matter the speed, as long as you watch the whole thing. As long as it's not finished, you're going to keep on learning, keep on watching that thing, and then this is your life, right? This is your life in an online class. Whee! So I hope you see that and it's making some sense. And these 2 little circles, that's called a final state. So at the end of the class, there's nothing more for you to learn, and so we call this a final state. That's where you want to stop. Okay, that's the stopping point for you as a state machine. All right, so one last example, then we'll get out of here. Let's count the words in a sentence using a state machine. All right, so here's the idea. I have a sentence, like we got something from the user. We got a sentence, like, hey, please enter some sentence. And so like in our answer variable, if I could spell answer, we said something. It's like, okay, hi, Mom. And so that's our sentence. It's stored somewhere. And what we would like to do is count the number of words in that sentence. So here is the state machine for doing it. It's a nice, it's an elegant way of doing this, I would say. So you can read the characters one by one and keep track of white space. That's what we're going to do. We're going to have this little arrow, and this arrow is going to point at the current character we're looking at. Darn it, put them all together. I want a separate arrow so I can move it. Yeah. So we're going to start here. Okay, we saw the H, we processed it. Okay, we saw the I. Okay, we saw the space. We're processing all of these things until we get to the end of the string. Okay? Sorry, the end of the sentence. String is a fancy word that means sentence in a computer. We'll talk about that with Python. Okay. So here's the key idea for the state machine that I'm about to teach you. White space separates words, so each character is therefore part of an old word or the start of an existing one. So every time you see a non-white space character, a non-space, you're either inside of a word or you're just starting a new one. Okay? That is the idea. Dun, dun, dun. And I think I should have said new there. That would make a lot more sense in my mind. That must have been a typo. All right. So here is how I want you to think about this. So we're going to keep some kind of variable. Be like, okay, I haven't seen any words yet. Like it starts at 0. And then I see my H. Okay, yes, I must be inside of a word. Yeah? I see an I. I'm still inside of the word. Oh, I see a space. A new word is going to happen soon. Now I see an M after a space. This is my second word. And I keep on looking at these characters, and I end the sentence without finding any new words. So that's the kind of process that I'd like to formalize in this little state machine, right? So let's start out being, we say, not inside of a word. That's our state. So like, if we see the I, we've already seen the H, so we're like inside of the word hi. We're looking at it. We're still counting this as one word. All right? So that's our first state, our start state. And we're going to stay inside that. Actually, let's talk about how we can transition out of it first. That's probably the most helpful. That was bugging me. Okay, so we're going to stay not inside a word as long as we see a space. But the second we see something that's a real character, like this first character here, we're going to be like, oh, I've seen a first character. I've seen a non-space character. See a non-space character. And then we'll say, oh, I must be inside a word now. Hey. And the second I see a non-space character, I'll like add 1 to my count. That's the idea. And so now we're inside a word. We're counting all the characters that make new words. Oh, this next character, well, it's still inside the same word, right? So as long as you see non-space, you stay inside a word. So like I see my H, so I've seen nothing. So I start here. I see an H, so I move here, add 1 to my count. Now I'm inside a word. Hey. And I'll just keep on counting. I won't add any more when I see the I. I'm going to stay inside of a word. But the second I see this space, ooh, I'm outside a word now. Okay? See a space. And that brings me here. There might be multiple spaces, in which case you want to stay outside a word as long as you see spaces. And this is actually the entire machine. Let's go through this example now. Let me erase these 0, 1s, and 2s. So here's the idea. We start out in our start state, having not seen anything. And then we see the H. So we follow this transition, and now we're inside a word. And we also, along that transition, we should add 1 to our current count, which started at 0. Okay, so now it's 1. And now I see the I. Well, that's still a non-space character, so I'm staying inside this state, the inside a word state. And then I see the space. Woohoo! Now I'm no longer inside of a word. I'm getting ready to see a new one, hopefully, if I ever see a non-space character. Okay, so hopefully you're following this. It's not too bad. I see the M, so now I was here, I see a non-space, I'm inside a word again, and because this is a new word, I add 1. Add 1 to my count. Okay? That's like always incrementing whatever it thought the size was. So then we stay inside a word, inside a word, inside a word. The string, or the sentence is over, and we give back our final answer. So that was 2. There were two words in this sentence. And so that's how you can make a complicated concept like counting words into a simple 2-state machine, which maybe it's a bit confusing starting out, but this is a gold mine for a programmer. It's like, okay, I can totally program this very simply once you have enough practice under your belt. So that is state machines in a nutshell, and that's all I have for you for this lecture. So we've talked about a bunch of different ways to do things, and then also some computational concepts. So hopefully you're going to make better arguments now, if you weren't already making perfect ones, and we are ready to use these skills, especially the state machine skills, in our programming lecture. So I will see you in that.